Good morning, everybody. Last time I reached the train station on time, and the train was on time. And this morning my bike was late. This is a different story. We talked about Bremsstrahlung, and we used the same scheme as we had developed. That is, we used Larmore's formula and had to evaluate, in order to get the spectrum, the acceleration of the charge considered, electron for example. And we made a simplification, right? We evaluated this acceleration in Born's approximation, just to simplify the derivation. The whole derivation is possible, complicated, more complicated. The scalings that come out are correct, the amplitude is not. What did we find? We found that the Bremsstrahlung emissivity, that is, the energy per unit time, per unit volume, per unit frequency, is determined by the square of the densities of the two contributing charges, the ions and the electrons. So I should say it's given by it's proportional to the number densities of both, right? And since they are both related, it's proportional to the square of free particles. It scales with the with what? With 1 over the square root of the temperature, and we have an exponential factor that cuts off the spectrum at a frequency that corresponds to the thermal energy of the electrons. This was the spectrum for thermal Bremsstrahlung. Now, of course, you could have other Bremsstrahlung as well, right? Bremsstrahlung in traffic or so. So this result with the exponential cutoff depends on the thermal distribution of the electrons, and if you had another distribution, any kind of non-thermal distribution, the spectrum would of course look different. Nonetheless, in many cases where you find Bremsstrahlung in the universe, it is thermal and is characterized by the exponential cutoff. You often find in the literature that the exponential cutoff is characteristic of Bremsstrahlung. This is correct, there's just one word missing. Okay, that was that. Do you have questions up to that point? Yes?
I have a rather general question, because when we consider Kepler's problem, then we had this potential energy versus kinetic energy balance, and we didn't consider any radiation. So I'm asking myself, if we now consider a particle, and it does basically the same thing as in Kepler's problem, but it radiates energy, and somewhere it has to lose this energy.
Yes.
Right? It has to lose kinetic energy or something. But so it has to kind of get slower, or the acceleration has to change. I don't know. But we didn't consider that. And that's why I'm asking myself, where exactly does the energy from the radiation come from?
All right, yes. So the question was about Kepler's problem. Did I understand this correctly? The question was, we did not take energy loss into account when we studied Kepler's problem in theory 1. So where's the energy coming from that is being radiated? And you didn't ask that, but I understand that's part of your question. Why did we not take any energy loss into account when we studied Kepler's problem? All right. The answer has several parts. The first is, yes, it's true. We evaluated the electron's orbit as if there was no energy loss and calculated the energy loss assuming that idealized orbit. Strictly speaking, this is incorrect, but the energy loss compared to the energy that is in the orbit is much smaller. So this is an approximation. And if we took the energy loss into account, we would not get one of the ideal Kepler orbits in that situation, but for example, an orbit that would gradually spiral into the force center. We did not take this into account when we treated Kepler's problem because In Newtonian gravity, there is no energy loss in that case. In relativistic gravity, there is, right? There are gravitational waves as well. And so, strictly speaking, you would expect that in general relativity, you do have, in fact, an energy loss also in gravitation, in the gravitational situation. However, in order to lose energy by gravitational radiation, you need to have a time-dependent quadrupole moment of the source. And in this case, where you have a planet, for example, of at most about 10 to the minus 3 times the solar mass, like Jupiter, the loss of energy through gravitational waves is very, very small, and we can neglect that. But strictly speaking, the situation is exactly the same. You have an energy loss, it's very small. If you took it into account, you would not get bound orbits anymore. And the energy is coming from the sum of kinetic and potential energy. And this leads to the curious fact that if you make an orbiting, if you make a particle that orbits in an attractive force field, lose energy, it becomes faster by the Virial theorem. All right, further questions on Bremsstrahlung? Let me then continue with what we started last time. We started with a situation that we have an electron flying through an isotropic sea of radiation. So there is one reference frame. Beautiful, right? Where we have isotropic electromagnetic radiation. I find it easier to think of that as an isotropic photon gas. I don't know about you, it's just a suggestion. So what do we assume? We have an unprimed frame here. And in this frame, we have electric field components, we have magnetic field components, and the isotropy means that in all directions, their average is 0. Now, of course, if you choose to move with respect to the rest frame of this radiation, isotropy is broken by Lorentz boosting. We further assume that electric and magnetic fields are uncorrelated, so that EIBJ equals 0 for all combinations of I and B, for I and J, sorry. Okay, good. And then we made an electron fly into that. And there was a subtle mistake in my last presentation, because I chose the flight direction of the electron such as to be parallel to the Z axis. This doesn't matter because we are assuming an isotropic sea of radiation in its rest frame, so we can rotate the rest frame of the radiation such that the direction of motion of the electron would always point in the Z direction. But last time I made the electron come from here, and then the equations were wrong. All right, so it's flying that way. Now I need to transform into the rest frame of the electron, and for that I'm using the Lorentz transform equations for the electric field components only, that's enough. So I'm using that in the rest frame of the electron. That's the one with the prime. Ex, Ey, and Ez prime are given by Ex, Ey, Ez, Bx, By, Bz in the following way. And now, and this was the mistake, now we have Ez prime equals Ez because that's the field component into the direction of motion. Okay. Now I'm using the Larmor formula in this form. It's 2e squared divided by 3c cubed, and now the absolute value doesn't matter, but this way it looks nicer, times the absolute value of the acceleration squared. Of course, now I can't evaluate this. Now I have to average over the acceleration, because the acceleration will change all the time. Right? So this is now what I have to calculate. Then I will encounter averages of field components E square, EB, and B square. And for those, I'm using that the energy density, for example, in the electric field, let me call this UE, let me call it U, is given by E squared over 4 pi. Now, because I am assuming isotropy, all field components will contain the same fraction of the energy. So this is, for example, 3 times Ex squared divided by 4 pi, same for Y and Z, in the rest frame of the radiation. Aha, okay, now I can insert this as 2e squared divided by 3c cubed. Okay, now we need to square this and that and add all of them. What happens is that we get a gamma square for 2/3 of them. Right? So by democracy, I'm writing gamma square out front, and then I have to take into account that this one does not have a gamma square. All right, then I get Ex squared average. That's going to be 4 pi times u divided by 3. That's going to happen for all of them. So let me add this factor here. That's common to all of them. Then I will also get mixed products. They're going to go away by our assumption of uncorrelated electric and magnetic fields. But then I will get a factor of b squared decorated with a beta square. And this happens for both of them. So in total, I get 2 times 1 plus beta square from squaring Ex prime and squaring Ey prime and adding them. And then I have to add this contribution. This has this factor. It does not have this factor. So we'll have to add 1 plus, I have to add 1 over gamma squared. But gamma squared is 1 minus beta squared. All right, that's it. That's what I wrote down last time, but maybe a bit too short. All right, so we get 2 plus 1 is 3. We get 2 beta square minus beta square is beta square. I'm pulling a factor of 3 out for cosmetic reasons. And look how beautifully we get our 8 pi over 3. E squared divided by c cubed u 1 plus beta squared over 3 times gamma squared. But I missed one thing. Because here I have just, for the acceleration squared, taken the squares of the field components. But the electric part of the Lorentz force has a factor of E over m, electron charge divided by electron mass, in addition to the field components. So I get another factor E square over me square here. And now you see I'm getting an e to the power of 4 divided by me square c to the 4th times c. But this I can write then as the Thomson cross-section times c times u times gamma square times 1 plus beta squared over 3. Do you believe all that? Do you find any inconsistencies? What I've written down here is the non-relativistic Larmor formula. And I've done all the rest of the calculation as if I could have relativistic electrons. Did I do wrong? Do you remember the relativistic expression for the Larmor formula? It has an acceleration squared. So if I pull factor of c square in here, I have beta dot square, and then I have minus beta cross vector product beta dot squared. This does not contribute if beta is pointing in the direction of beta dot. But here what I'm studying is the friction of an electron experienced by flying through photons. And that friction points exactly opposite the direction of motion. So beta vector multiplication times beta dot is in fact 0. And in that case, the relativistic Larmor formula looks exactly like that. Right? Okay, good. That is fixed. Therefore, even though we pretend to be non-relativistic, we can use the same result for the relativistic case. Now something else. This is now the radiation power. Power is important. In the rest frame of the electron. Right? We have taken great care to transfer ourselves in the rest frame of the electron. This is not what we wanted to know. So we have to Lorentz transform back, right? But the power is an energy difference divided by a time difference. And both time and energy are the zero components of a 4 vector. So they transform in the same way. So there is no difference between the power of the electron emitted in its rest frame and the power of the electron emitted in the rest frame of the photons. There would be a big difference in the energy. There is not in the power, right? Because the time and the electron's time and the electron's energy emitted during that time transform in the same way into the rest frame of the photons. This would not be the case if we had calculated the differential Larmor power. Right? If we had asked for the Larmor power emitted per unit solid angle, that would depend on the direction around the electron. That would transform differently, right? Because solid angles transform differently. But here we are safe, right? We ignored the directional information, and we can use the same expression in the rest frame of the electron and in the rest frame of the radiation. So I should have written P prime. I did not. For a good reason. I should have written X double dot prime. I did not, for no good reason. But now we can use this expression here for P as well. Okay, good. Now we are back in the rest frame of the radiation. And so we can here say in the rest frame of the radiation, the electron loses this power here, this energy per unit time, because this is the gain of power in the radiation field. It's the loss of power for the electron. Okay, there's another thing we need to take into account, because the electron, as it carries around the Thomson cross-section, at the same time is collecting photon energy, right? So this is the emission power. We also have an absorption power. This we need to subtract in order to get the power balance for the electron. So in order to be specific, I need to write down, this is the emission power. The absorbed power is just C sigma T times U. Right? The energy per unit time that the electron absorbs is given by the volume per unit time that the electron flies through, or rather that the photons fly past the electron, times the energy density in the radiation. All right. So the total power is this, and we have C sigma T U gamma square 1 plus beta square over 3 minus 1. Minus 1 over gamma square now, since I pulled the gamma square out. So I'm using the exact same trick as before. Now you see the 1 goes out. We have beta squared over 3 plus beta square, so that's 4/3 beta square. And we have, as a result, 4/3 beta square gamma square C sigma T U. All right, that is a very nice formula, right? We have a Lorentz boost that gives us a factor of gamma square. We have the factor of C sigma T, that's the volume per unit time that is covered by a Thomson cross-section moving with the speed of light as appropriate for the photons. And we have the energy density of the photons here, which gives rise to the acceleration of the electrons, thereby to the emission of the electrons, but also to the absorption. This is per electron. Okay. If you wanted to know, for example, the emitted power by a population of electrons, we would have to take into account that now we have to multiply this with the electron number density, which we would have to split up into contributions by electrons with a velocity beta. All right, we will get to that. Now, you can turn this into friction force for the electron. Right? This is the amount of energy lost by the electron per unit time. Or rather, this is the energy gained by the radiation field from one electron per unit time. If I change the sign to minus here, then it's the energy lost by the electron per unit time. So if I now specify with d epsilon dt, the energy lost by the electron, this is minus 4/3 beta square, gamma square, and so on, just this thing copied. But now if I change this to the energy lost per unit path length, this is the friction force. Right? Because force times path length is the work exerted on something. So if I transform this to d epsilon dx or dz, right? It's flying in the z direction. Let me do it like that. This is going to be the friction force. F. So now this is d epsilon. Yeah, d epsilon dt, dz. So you see, if I take this result here and divide it by the electron velocity, I will get the friction force. So what is this? This is minus 4/3 beta. Now I have divided by beta. I should have divided by the velocity. So now I'm getting a factor of c squared instead of c. And I get this here. So you see, it's a friction force, at least in the limit where you can neglect the velocity dependence of gamma square. It's a friction force that is proportional to the electron's velocity. It's like the simplest assumptions we've usually made in mechanics 1, right? Friction force proportional to the velocity. All right, and then you can calculate the energy loss and so on and so on. How the orbit decays and so on. Right? What it tells you is that if you look at a single electron here, there will be an acceleration proportional to minus the velocity, which will lead to an exponential decay of the electron's velocity. All right? Friction force. Yeah.
Why does the epsilon dt have a different sign than P? P is also like P emission minus P.
P is the emission of the electron. So that is the energy put into the radiation field per unit time. This is the energy lost by the electron per unit time. Okay, that was a side remark, right? You can just turn this into a friction force, and the friction force turns out to be proportional to the velocity. I'll calculate a friction coefficient, and so on and so forth. This is interesting. For example, if you consider a charged particle moving through the universe, that's what they often do, right? What they like doing. Then they have to go through a sea of radiation anyway, right? Because there is the cosmic microwave background. The friction is not very strong, but the path length is quite enormous. Right? So you have a small friction force acting over a very, 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 very long distance. So charged particles can't just propagate through the universe as if there was vacuum. Right? There is a medium. This medium is inevitable. It's the cosmic microwave background. You will find a problem on the next problem sheet, right? Just to calculate how far does it get, right? How far does a highly energetic but charged particle travel through the universe before it finally loses all its energy? Good. So far, so good. Do you have questions up to this point? Yes. Yeah. The question was, why is P invariant under Lorentz transforms? The reason is P is a ratio of components, of zero components of two 4 vectors. Right? The energy is the zero component of a 4 vector, time is the zero component of a 4 vector, both transform in the same way, so their ratio remains invariant. Again, right? This is different if you have a differential emission, differential in terms of direction. Then you do have the Lorentz transform of the solid angles. All right. Let me now come to Compton scattering. So far we have looked at Thomson scattering. Now we are going to look at Compton scattering. The point is, when we looked at Thomson scattering, the situation was this, right? We looked at an electron, and there was an electromagnetic wave. For some reason, I keep thinking of gravitational waves. Why? I don't know. So there's an electron, an electromagnetic wave is coming along. It's going to accelerate the electron in this way. Because of that, we neglect momentum transfer of the electromagnetic wave on the electron. That is because in classical electrodynamics, in the vacuum, electromagnetic waves are transverse. And they shake the electron left and right, but they don't accelerate the electron in their direction of motion. This can't be quite true. If we have a very energetic photon, for example, now we switch to the photon picture, if we have a very energetic photon which hits the electron, it will pass part of its momentum on the electron. How much? There's a different contribution to energy exchange between a photon field. So now I keep saying photons instead of electromagnetic radiation, right? We switch to the photon picture now. So there must be another contribution to energy exchange between charges and the photon field. How much? Right? How much is there? Okay, and for studying this, we have to study Compton scattering. Compton scattering, and here we take the momentum exchange between the photons and the electrons specifically into account, which we had neglected in Thomson scattering. So in this sense, Thomson scattering must be a limiting case of Compton scattering, the limiting case of negligible momentum exchange between the photons and the electrons. Okay, now the picture I have in mind is electrons are red, we said. So there's an electron, photon coming along, photon has a momentum h bar k, electron has a momentum p, and after the scattering event, photon will have a momentum h bar k prime. So it lost some of its momentum in this direction. So the electron must have gained some momentum in this direction. Do me a favor and don't measure this, right? All right. Now, let me write down two equations that we have to satisfy. So we need to satisfy energy conservation, right? The electron energy, which is now E again, because there's no E electric field anymore. The electron energy plus the photon energy must sum up to the same values before and after, and the momenta. And for reasons, I'm multiplying the momenta with the speed of light. Let me indicate the direction of motion of the electron the photon, before the scattering event by a unit vector E hat. and this is the momentum equation, momentum conservation equation, multiplied with the speed of light. And I'm multiplying this with the speed of light because I need to, or I should take the dispersion relation of the photons into account. Omega over c is k. It's the wave number. And if I multiply this by c, then I can express the photon momentum also by h bar omega. Okay, good. That's equation number 1, that's equation number 2. Now I'm sorting equation number 2 such that Cp prime is on one side and the rest on the other, and I square it. So I get C square P prime square equals C square P square plus H bar square, H bar omega E minus omega prime E prime square, and I get the mixed term, which is plus 2ch bar P omega E minus omega prime E prime. That's just equation 2, sorted, squared. Now let me use the relativistic energy momentum relation, which says E square C square P square plus M square C to the 4. So let me add to this equation M square C to the 4, and then just replace these terms by the squared energies. Okay? I know you can't wipe on, or maybe you can wipe. Most of you are writing on electronic devices anyway now. Aha, very good. All right. So now we have turned the momentum relation into an energy relation. We have another energy relation to satisfy. We can use that to eliminate E prime. So I'm going to use equation 1 to write E prime square as E plus H bar omega minus omega prime squared. So I'm now using, in addition to momentum conservation, energy conservation, and I write the E prime here by what I get for E prime if I solve this, the energy conservation equation. Okay. Now, of course, the E square, yeah.
I have a question. Are we making an approximation by using energy and momentum instead of?
No, we are not. No, we are not. So the question was, is there any approximation entering because we're using energy and momentum conservation separately? And this is not the case because what I'm using is just this. Right? The 4 momentum must be conserved. And now I'm splitting the 4 momentum into 1 plus 3 components. And the first component is the energy conservation. The following 3 components are the momentum conservation. All right, so if I square this, the E square goes away. Then I'm getting a term that looks almost like that one, but not quite. This contains direction information in the momentum part. This does not. So if I subtract the square of that from that, the squares will go away, but the mixed terms will remain. Right? The term with omega times omega prime, or minus 2 times omega prime, E hat times E hat prime, this will remain. The other contributions will cancel, and from here we will have a minus H bar E omega prime without the directional information. Okay. So let me write the mixed term of this square on the left-hand side. The left-hand side is this one, right? And bring the square of this term to the other side. Then I get 2 h bar square omega prime, 1 minus cosine theta, where the cosine theta is now the angle between the incoming and the outgoing photon directions. Okay? So I'm getting this cosine theta from this expression, I'm getting the 1 from that expression squared. Mixed term is over here, e squared is cancelled. What remains is 2c h bar p omega e hat minus omega e hat prime. Okay, now let me divide this equation by 2e h bar. All right. Looks like there's a sign error. No, there is not. Okay. So then omega minus omega prime remains on the left-hand side. I'm dividing by 2e h bar, so we have left here h bar omega prime divided by e times 1 minus cosine theta and plus Cp divided by E Okay, this equation is how far we get by only using energy and momentum conservation. Now, what I'm going to assume is that the electron was at rest before the scattering event. So then E is mc squared, it's the rest energy of the electron, and P is 0. And then this term goes away. And I get omega minus omega prime is, now you see there's a ratio of h bar omega divided by mc squared appearing. That's the photon energy divided by the rest energy of the electron. I call this epsilon now. And the epsilon is supposed to be very small. Right? The photon energy is supposed to be very small compared to the rest energy of the electron. We have to assume this anyway. I'm going to comment on this. So here I have epsilon omega bar 1 minus cosine theta plus 0. So now epsilon is this. Let me come back to that for a moment. If the photon energy was so high that it was comparable to mc squared, we could not use the classical photon picture anyway, because then we would have to go to quantum electrodynamics and take into account that photons with that energy, with so high energy, would be able to create positron-electron pairs. So we have to stop before that anyway. Okay? If we were to go further, we would have to study Klein-Nishina scattering instead of Compton scattering. That's the quantum electrodynamical equivalent of the Compton scattering process. So we can safely assume epsilon to be small. Epsilon much less than 1. Okay, let me reorder this a little bit. Bring this omega prime to the other side, the rest to the other, and so on, and find omega prime divided by omega is 1 over 1 plus epsilon 1 minus cosine theta. This is the relative frequency change of the photon. And I'm going to write this now in accordance with our approximation as 1 minus epsilon times 1 minus cosine theta. So I'm making a first order Taylor expansion in epsilon, assuming that the photon energy is small compared to the electron's rest energy. Yes?
What is the theta now that the electrons at rest?
Sorry?
What is the theta now when the electrons at rest?
Eta?
We assume now that the electron is at rest before the scattering.
Mm-hmm.
So how do we find the angle?
The angle is between the directions of the photons before and after the scattering event. That's the photon scattering angle. So I should write this here. All right, and this is this here. All right, so photon scattering angle. Now let me briefly finish this and then we have a break. I would now like to average this energy, relative energy or relative frequency change, omega prime over omega, over photon scattering directions. So I want to average this over theta. But then this means that I have to average this over the angle dependence of the cross-section. But this we know, it's the differential Thomson cross-section. Right, so I have to average this in the following way. Omega prime divided by omega average. This would be 1 over sigma t, average over solid angles, Re square over 2, 1 plus cosine square theta, 1 minus epsilon, 1 minus cosine theta. That would be the average, right? And what I have written down here is d sigma t with respect to d capital omega is the differential Thomson cross-section. If you were looking at Klein-Nishina scattering, for example, that would change. Since we are in the classical limit, we can use that. All right, that's the usual solid angle integral. It's d phi sine theta d theta. So it's a d phi d mu with mu equals cosine theta. There's no phi dependence in the expression, so I get pi Re squared divided by sigma t after the phi integration. Just gives me a factor of 2 pi. And then what remains is a mu integral from minus 1 to plus 1 over 1 plus mu squared, 1 minus epsilon, I'm writing this a little differently, 1 minus epsilon plus epsilon times mu. So this I need to carry out now. Now, any odd power of mu appearing in the integrand would then be integrated to an even power evaluated at plus and minus 1, which would cancel. So we only need to take into account the even powers of mu now, right? Because the odd powers go away anyway. So which even powers do we get? Well, we get mu to the power of 0, and we get a mu squared. So I get 1 minus epsilon times mu to the power of 0. And I get 1 minus epsilon times mu to the power of 2. Those I have to take into account. The others are odd powers of mu and go away anyway. So this is 1 minus epsilon times something. Now, 1 plus mu square integrated over mu from minus 1 to plus 1, what is this? Well, the 1 integrated from minus 1 to plus 1 d mu gives me a factor of 2. And the mu square integrated from minus 1 to plus 1 over d mu gives me a factor of 2/3. So I'm having 2 plus 2/3. This makes 8/3. Isn't this beautiful? 8 pi divided by 3 times re squared. This just cancels the Thomson cross section, and we are done. Let's have a break. 5 minutes break. So, let's come back. This was the result of the previous average. And there was the question in the break, and I was waiting for that for a little bit. Why can we use the differential Thomson cross-section to go about Compton scattering? Why is that? Well, this is because we are in the classical as opposed to quantum electrodynamical limit. If you want to get the precise answer, you need to treat Compton scattering in the quantum electrodynamical limit. And then you see that in the classical limit, the differential cross-section for the Compton scattering process equals the differential cross-section of the Thomson scattering. This is why we could do the average in this way here. All right. Now what is this here? Well, if you look at the energy change in the photons, this is now the energy change in a single photon. Because we looked at the scattering of a photon of an electron divided by the photon energy E gamma, then this is minus epsilon, right? Because the energy change is h bar omega prime minus h bar omega. So this is this result minus 1. And so this means that the energy change per photon is minus epsilon h bar omega. That was the photon energy before the scattering event. Okay. This is now the energy change per photon. I would like to transfer this or to rewrite this as an energy change in the photon distribution per unit time. Okay, how do I do that? I want to know how much energy do the photons lose because we have a minus sign here, due to Compton scattering events per unit time. And in order to find out, what do I have to do? I will have to multiply this with the number of photons that an electron will encounter per unit time, right? Okay. So this is epsilon times h bar omega, the energy loss of a single photon. Now, times C sigma t times the number density of the electrons. Okay? So the photon will fly per unit time by c dt. It will encounter all the electrons that are contained in an area of sigma t. So this is the volume of the photon covered per unit time, and this is the number of electrons it's going to encounter per unit time. All right. Now let us look at the energy gain per photon. That's the energy lost per photon. Now the energy gain per photon, we can calculate from the radiation power of the electron moving through that sea of radiation. Right, let me recall that result. That's 4/3 beta square gamma square c sigma t times u. That was the net power emitted per electron Now, how do I transfer this to an energy gain per unit time per photon? Right, first of all, I need to multiply this with the number of electrons that the photon will encounter per unit time, and I have to divide this by the number of photons per energy density. So I have to, I'm writing this down first of all. So that's 4/3 beta square gamma square C sigma t h bar omega times NE. So in the course of going there, I divided this by the number density of photons, which is the energy density divided by h bar omega. That's the energy density of the photon distribution divided by the energy of a single photon. So by dividing through that, in other words, by multiplying with h bar omega divided by u, I'm getting now the energy gain of the photon distribution per photon. All right. So now I have the energy gain. I have the energy loss transformed to the same unit, right? Per unit time per photon. Now I can compare. Or I can combine both of them. Let me go down here. So this is now the energy change per unit time per photon. And this is going to be the energy gain per photon minus the energy loss, so minus epsilon h bar omega c sigma t times NE. All right, let's pull this together. So this is c sigma t h bar omega NE 4/3 beta square gamma square minus epsilon. All right, now, I said before, right, if we have a distribution of electrons over velocities, which we will usually have, then I will have to average this beta square gamma square factor here. And by this average, I mean the following thing. Beta square gamma square average, this would be 1 over the total electron number density times the integral over velocities. Now the electron number density as a function of velocity beta times beta square gamma square. All right, now if I replace this, then I will get the mean energy gain per photon due to the electron population, which has a number density Ne here. All right. Okay, now let's apply this. Right? Let's play with this equation. And think about the following situation. Let's assume we have an electron population inside a photon population. And we have a photon gas, we have an electron gas. The photon gas has temperature T gamma, and the electrons have temperature TE. And I wonder when do we have equilibrium between the two, which must mean that there is no net energy exchange between the electrons and the photons anymore. And I'm assuming for simplicity that the electrons are non-relativistic. So then beta square gamma square is in very good approximation an average over beta squared. This is 1 over c squared, an average over v squared. Now I'm assuming a thermal electron distribution as well. And this means that I can use that MEV square divided by 2 equals 3 over 2 kBt, right? That's the equipartition theorem in thermal equilibrium, right? Each degree of freedom gets 1/2 of kBt as an average energy. Should write this in this way here. Okay, so I get for the mean square electron velocity 3 kBt over MEC squared. That's a small number, of course, right? It's the thermal energy of the electrons, kBt, divided by their rest energy. But of course, right, we expected the electrons to be non-relativistic and therefore beta to be small. Okay, good. Now, we need to do the same thing for the photon gas. Because we would need to average over h bar omega. And remember what epsilon is, right? Epsilon is h bar omega divided by MEC squared. So we need to know what is the average value of h bar omega and of h bar omega squared for a thermal photon gas with temperature T gamma. All right. This is relatively easily calculated if you take into account that the occupation number of a photon state is just given by the Bose-Einstein distribution, where the x is now h bar omega divided by kBt gamma. Okay, now you can convert this occupation number here into a photon distribution over omega. That's going to be the Planck law, of course. I guess you've seen that, right? So then I can use that in order to calculate what is h bar omega. And that's going to be 3 times the Riemann zeta function at argument 4 divided by the Riemann zeta function at argument 3. This is because we get integrals of this type and they are given by that, right? This is why the Riemann zeta function appears here, and so on and so forth. At the same time, and this 1 over zeta 3 just comes from normalization. And we have to normalize the probability distribution of the photons, and this is why the 1 over zeta 3 appears here. And then we have the average of h bar omega squared. That's 12 zeta to the power of 5 divided by zeta to the power of 3. Same normalization factor, but since we have this thing out front here, we get a different expression there. Aha. Well, then we can directly insert this, right? Yes, C, sigma T, and E, they do not respond to the average. I can write them out front. Now I get 4/3. This average, that's that one. Where am I? So I get 4/3 times this. So this is 4 kBt divided by MEC squared. Now I'm here, but I have so far not taken into account that I also need to take the average of h bar omega. If I insert this averaged over the photon distribution, I get 3 zeta to the power of 4, zeta to the power of 3. That's the first term. Now in the second term, I need to take into account that this epsilon here is h bar omega divided by MEC squared. I need to multiply with h bar omega, so then I need to insert the average of h bar omega in brackets squared divided by ME squared. These are not just numbers. Certain factors times the mean photon energy. I'm sorry for that. So here I'm getting this factor as well. Now I'm running out of space, so let me write this underneath. So this is going to be kBt gamma squared times 12 zeta to the power of 5 divided by zeta to the power of 3. Isn't this nice? Now we can just pull things out front. Let me write them in this way. C sigma t times Ne, 12. I'm pulling all of that out, right? So that just one remains here. So I have 12 zeta of 4 divided by zeta of 3 kBt electron kBt gamma. Let me specifically distinguish the two. Divided by MEC squared. Okay. Now 1 remains for this term. Then I get zeta of 5 divided by zeta of 4 times T gamma over T electron. Okay? This is not beautiful. Now, let us first check the dimensions. C sigma t times Ne. C sigma t is a volume divided by time, the volume per time. I'm multiplying this with a number of electrons per volume. So this is the number of electrons encountered per unit time. So this has unit 1 over second. This is the thermal energy. That's the thermal energy of the electrons. This is the thermal energy of the photons. I'm dividing this by the rest energy of the electrons. So this is an energy. It's an energy per time in total. And we have this numerical factor here. So all of that is just a normalizing factor. And now we look at the equilibrium condition. Right? The equilibrium condition is that dE gamma with respect to dt equals 0. Let me continue over here. So now we have equilibrium between, let me very briefly write, thermal electrons and thermal photons. The condition is there's no net exchange anymore between the energy exchange anymore between the electrons and the photons. So this means that the right-hand side needs to be 0 as well. And this means that the photons and the electrons must have different temperatures, because the zeta function of 4 is different from the zeta function of 5. No protest? You get different temperatures in thermal equilibrium? Well, try to get a patent for it, because this is a perpetuum mobile. What's wrong? What's wrong? We study thermal equilibrium between our thermal photon distribution, our thermal electron distribution. We get equilibrium at different temperatures. Tell it to Minister Habeck. This will solve all energy problems. What's wrong? What did we do wrong? We took a lot of care to calculate the energy loss of the electron in the photon Z. We did a lot of care to calculate the energy gain of the photons, the energy loss of the photons by collisions with the electrons. We took the balance of the two. We took the non-relativistic limit. There's nothing evil in that, is there? And we get a result that is completely incredible. Why? What's going wrong where? Do you have an idea? It must be wrong, yes?
Is it maybe that we assume separate thermal distributions for the electrons and photons, so that we maybe need to adapt their distributions?
That's an approximation. It's getting very close to the answer. But let's assume they have already similar temperatures, and we look at the final step of equilibrating them two. But this goes a long way towards the right answer, yes. Think of what we have assumed. We have assumed the equipartition theorem for the electrons. What are the conditions for the equipartition theorem? It's just that the electron kinetic energy is homogeneous in the electron momentum. You almost cannot break this. So the equipartition theorem, that's rock solid. So in other words, this expression here that relates the mean square electron velocity to the electron temperature, that is rock solid. Right? That just uses the equipartition theorem. See, we are not even using the Maxwell-Boltzmann distribution. Right? We are using something more fundamental. We are using the equipartition theorem, which does not need the Maxwell-Boltzmann distribution. It holds under the conditions of the Maxwell-Boltzmann distribution as well, but it is much more general than that. So there's no problem with that. But what do you say about this? Who of you, yeah? Goes a further step into the right direction. There's something wrong with this here. What is wrong with that? Who of you had already a course in statistical physics? It's up to you now.
I'm not the only one, I'm sure.
Yeah, okay. You need to take into account that there is a chemical potential between them. Right? This is the photon distribution without the photons interacting with anything. That's a free photon gas. We do not have this. There must be a chemical potential between the two. In other words, we have to replace pure Bose-Einstein distribution by this, including a chemical potential. Yes?
Sorry if I should know this already.
No, 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 no. A chemical potential is the amount of energy you need in order to change the number of particles in a system by one. Did we have this in theory too? No, I don't think so. Suppose you have a mixture of different gases, right? And you want to change the number of particles of one type in the other part of the system. You want to add a particle there, or you want to subtract a particle there. Then you may need some energy. And this is the chemical potential, right? The amount of energy you need per particle in order to add it or remove it from a system. And this is exactly the point, right? You need to introduce a chemical potential for the photons in this case, in order to take into account that they do not form a free photon gas, but a photon gas in interaction with an electron gas. Okay. You will recover, or you discover this on the next problem sheet. Yes?
Are we not assuming that the scattering is elastic?
We are also assuming that the scattering is elastic, yes. Because in the presence of the electrons, changing the photon number costs or gives some energy. Right? Because they also attract each other, or repel each other, the electrons. Okay, so I'm going to make a problem from that, right, that you can solve, and then solve for the chemical potential, and then you can actually calculate what energy it will take in order to create or absorb or remove a photon from that distribution. Because you must have both, right? You must have equilibrium between them after a while, and you must have equal temperatures, because that's the definition of thermal equilibrium, right? Equal temperatures between the two. And you see here that this comes at the cost of having to introduce chemical potential for the photons. Now, have you ever seen a spectrum of the cosmic microwave background? And I've been talking all along about this, right? The microwave background is everywhere, also in this room. In each cubic centimeter of volume here in this room, there are 402 photons of the cosmic microwave background. The cosmic microwave background is everywhere. So you can measure the spectrum of the cosmic microwave background. You can measure it extremely well, right? Because if you have 402 photons per cubic centimeter and you put a detector somewhere, you have an enormous number of photons per unit time that fly through this detector. It's an extremely well measurable spectrum. And it is an ideal Planck spectrum. We see no deviations at all from that. Although there must be some electrons in the universe. How can that be? How can it be that we discover, first of all, this here, right? That for any electron distribution equilibrium with a photon distribution, temperatures must be equal and the photons must acquire a chemical potential, therefore a deviation from the ideal Planck spectrum. This is what we just found. And we measure, not we, but other people did, got the Nobel Prize for that, that the cosmic microwave background has an ideal Planck spectrum. How can both of that be true? We talk about this next time. And you will find a problem about this, right, that asks you to calculate the chemical potential of the photons. You will probably need some numerics for that. We'll see about this. Doesn't hurt. You will encounter the polylogarithm function. Doesn't hurt either. All right. Now, what I had actually been planning to do, but okay, now the time is up, was to go through the theory of emission lines, emission and absorption lines. So for that now we have to take another step of generalization, namely that the emission and absorption of individual photons is a quantum process. Right? So far we did several steps. We started purely classically. Now today we introduced the photon picture in order to treat Compton scattering. Now we have to take into account that the absorbing thing may have internal degrees of freedom that are governed by quantum mechanics. So in order for next time, to prepare for next time, I'm asking you to do the following thing. I will build upon two ingredients from quantum mechanics, and I will of course repeat them next time and so on. But if you want to prepare, have a look at the quantum transition rate from one state to the other, and the result that this looks like this. This is Fermi's golden rule. What does it say? It's called Fermi's golden rule because it's due to Pauli, but anyway, prefactor, doesn't matter. Now we have the square of a transition matrix element. This is not surprising, right? Because this gives you the probability for transition from state N to state M. N and M stands for a certain collection of quantum numbers. That could be the quantum numbers that characterize a hydrogen orbit, any hydrogen orbit. Right? So then we have a perturbation Hamiltonian. The perturbation Hamiltonian comes from an incoming electromagnetic field. In other words, what we are looking at here is, now the word radioactive crosses my mind, but no, of electromagnetic transitions between two quantum states of, for example, a hydrogen atom. Okay? And then this is the Dirac delta function here, and omega nm is Em minus En. These are the energies of the states N and M divided by h bar. Okay, so what this says is you will get a razor-sharp line at the transition frequency with a probability that is given by the transition matrix element times some phase-space factor 2 pi over h bar squared. Okay, that's Fermi's golden rule. It's not difficult to derive, right? These are the states of the unperturbed Hamiltonian. So what you're looking at is a result of first-order perturbation theory and quantum mechanics. So if you do time-dependent first-order perturbation theory and quantum mechanics, you get this result relatively easily. If you want, have a look at that. You find it everywhere in any cookbook on quantum mechanics. Okay, the other thing I would need next time is that this perturbation operator for these electromagnetic transitions looks like E over MEC. What does it look like? Vector potential of the electromagnetic field times the momentum operator of the electron times the spatial variation of the phase of the electromagnetic vector potential. We will need these two things next time. I will explain next time qualitatively where they are coming from. But if you want to have a look in advance, these are the things we are going to need. Fermi's golden rule and the perturbation operator here under an incoming electromagnetic field. All right? It's Wednesday. Have a nice weekend.